Here we're going to look at visualizing total mechanical energy and kind of making sense of the actual physical motion for the block on the spring, connecting it to our potential energy function. We can see down here. We'll get to that in a moment. And specifically, we're also going to take a look at what happens when we are at the 50% potential and 50% kinetic point. It's a question they often ask for a multiple choice question or as part of the AP test at some point. So let's take a look at what we have. So we're picking up our analysis here, our visualization, where the block has just hit position x equals 0, so the unstretched spring position. It has its maximum velocity, and it is going forward to where it's going to come to a stop at this point. No kinetic energy. Have all potential energy. Potential energy is 1/2 kx squared, so that becomes 1/2 k a squared. And we started with all kinetic energy, right? No potential. At some point in time, we would have this 50-50 situation, and that's the point we really want to think about at the bottom. Where is the block going to be when the energy is equally shared between kinetic and potential energy? The rest of the illustration here then is simply the return half cycle. So this would be half of a period of motion, right? We go back in this direction till we have a Vmax here going to the left, and that is half a cycle. So one complete cycle, one period of motion, is when it comes back to where it started, so that would be all the way back to the position here at the top. Well, if we look at our potential energy function over this first, actually quarter of a cycle, right? So we're at a quarter of a cycle here. This would be from, I can get this in to hopefully illustrate, from here to here would be one quarter of the period of motion, right? So for that type of motion, the potential energy function goes with what we show here, right? No potential energy right at x equals 0, maximum potential energy at x equals a. Now, if, for example, let's say that represented 100 joules, at some point in time, it would be at the 50 joule mark. So get this down, get this representation down, that because the function, the potential energy function, is nonlinear, we are definitely not at the halfway point. And the halfway point will definitely be an option for you on a multiple choice question, or if this type of concept is asked on the AP test. So the last thing we have on this short page of notes is to look at where is the block specifically at the halfway point. Well, the trick to solving this is to only focus on the potential energy. Don't use kinetic energy at all. So even though it's the half kinetic energy, half potential energy point, let's focus on the half potential energy point. If we do that, then we're looking at when is the function 1/2 kx squared going to equal 1/2 the total energy that was available in this problem, which is the 100 joules. Remember that 100 joules is being shared between kinetic energy and potential energy as the block goes through its oscillation. Now it's very simple. As you can see, the math here shows we get x squared equals a squared on 2. We solve for x, we get a on root 2, or 0.7a. So it's roughly 70% of the way to its maximum acceleration when the energy is being shared equally. So, as I said, relatively short, relatively easy page of notes, but it does appear on many test banks, and I wanted to make sure you had seen this explicitly in your notes.